so yeah, this is the final lecture of the morning, so then we are going to have the lunch break. Okay, so please start.
Thank you. Yeah, so I'll continue again the discussion. I was planning indeed today to start with the SYK model, but since we had this great discussion about sort of the connection, at least the questions that show up if we start thinking about de Sitter space, I lost a little bit of time on my schedule, but I think it's great that we already have sort of asked questions. And the main lesson, at least of the first lecture, is that indeed if you start comparing what happens in ADS-CFT with what we should have to expect for de Sitter space, it's really that in de Sitter space, the energy spectrum is going to be bounded. Also, the entropy is going to be bounded. And both of those properties are not properties of ordinary CFTs. One thing that I briefly want to introduce still is a way of thinking about ADS-CFT in low dimensions, which I briefly mentioned at the end of yesterday's lecture. Namely, that there's a very universal structure that shows up, especially if you start looking at the heavy states. And there's an actual sort of a natural way of capturing that universal structure. And part of the universality of two-dimensional CFT in particular is coming from the bootstrap. In combination, indeed, with sort of clever arguments, some of which go back indeed to John Cardy, who showed that if you're thinking about the high energy spectrum of a two-dimensional conformal field theory, you can actually predict, again, in terms of the central charge, how the spectrum behaves. And the argument, indeed, is sort of one of the first bootstrap arguments, where you look at the torus partition function. Because, indeed, there's this Virasoro symmetry, and I mentioned, indeed, you can sort of classify the spectrum, or at least organize the spectrum in terms of highest weight states, labeled by some conformal dimension for the left movers and for the right movers. And the thing we're interested in is what is the spectral density as a function of this H and H bar. But now if you look at the torus partition function, you can decompose it basically in the characters which are the traces over each of those representations of the Virasoro algebra for H and H bar. But now the idea is that there's going to be a regime where you kind of know that the partition function simplifies. For example, if you indeed go to very low temperature, then you would expect that the ground state is going to be the dominant contribution to the partition function, because the higher energy states are basically Boltzmann suppressed. And basically you can show that a bit more formally, that in the low temperature limit, that this partition function sort of just factorizes into the product of two what we call vacuum characters. So in modern parlance, we call this sort of the vacuum conformal block dominance. But this is only true indeed in low temperature. And then there's another property of two-dimensional conformal field theories, or conformal field theories more generally, that these characters basically, they form a complete basis of sort of essentially things that you can associate with the torus partition function. And the torus partition function famously has two ways of looking at it, where you either cut open the torus in one direction or in the other direction. So you have a modular transformation that acts on this parameter tau, which is the shape of the torus, by tau to minus 1 over tau. And then you can decompose the vacuum character, should be decomposable in terms of the other characters after you do the modular transformation. And that decomposition is known as the modular S matrix. So if you combine this particular equation in this limit, you're going to get information, because tau to minus 1 over tau actually exchanges, there's a vector of I here maybe, exchanges beta and 1 over beta. So it exchanges the low temperature and the high temperature limit. And therefore, what you're going to deduce is that this rho of H and H bar is basically given by the product of this thing that's the modular S matrix, like that. So you deduce this particular formula. So now the task is to actually determine what those things are. But this is the prime example of what we call a bootstrap argument. There was a
modular
the factor of I, yeah.
And I guess for tau bar you would also like a minus perhaps, right?
Sorry?
In that equation? So
There's I dropped the minus C over 24 here.
No, for minus tau bar will be I beta.
Okay,
right?
sorry, thank you.
So that will lie on the upper half plane.
Is that what you're saying?
Yeah.
Good, thank you. Good, it's good that someone's paying attention here. Factors of I has never been my forte, although factors of I are going to be important today. So this is one comment. Another comment, which actually, to be honest, at least for me, was something that sort of started already popping up in my thinking about ADS CFT a while ago, that there's a convenient way of parameterizing essentially all the universal things that you can sort of derive by generalizations of this argument. It turns out that by generalization of that Carty argument, you can even predict what the OPE coefficients of a CFT are, even if the CFT itself is a thing you don't know. But with a similar argument, you can actually deduce the structure of the OPE coefficients for large enough conformal dimension. And all of that basically converges to essentially a unique, you can call it a CFT. And it turns out that CFT, maybe I'm going to call it Virasoro CFT. But the Virasoro CFT, which captures those universal properties, is given by the Liouville action. And so it's an example of a CFT, but it turns out to be that this particular Lagrangian, which is sort of a convenient path integral representation, if you wish, of a theory whose characters and whose properties capture sort of the universal maybe there's a factor of 2 here. I'm not 100% sure, but so it looks like a free scalar field, but then indeed with a thing that we call the background charge and an exponential coupling. So this is it's called the Liouville potential, but it has a coefficient typically in front of it. So let me still write that thing down. So this is a Lagrangian. You don't need to know too much about this theory, although it actually will play a pretty important role in what I'll be talking about. So I'm just going to write down the formulas that you need to know about this theory. This thing is a coupling constant. So if B goes to 0, this theory becomes weakly coupled. And it turns out that there's a direct relationship between this Lagrangian. If you start quantizing it, it's going to be a CFT with a central charge that's going to be 1 plus 6 Q squared, where Q is B plus 1 over B. So again, if B gets small, Q gets large, C gets large. So that's the weakly coupled regime of this theory. Sorry, other questions? Sorry? This defines Q. It turns out to be somewhat useful to have that Q in there. Because, for example, another thing you can do in this theory is to write down vertex operators as just exponentials of that field phi. And it turns out that the exponentials of this thing indeed are primary fields of this theory. I should mention again, of course, the Liouville action showed up in Polyakov's paper, famously, where he showed that if you do non-critical string theory, this is sort of the natural theory that describes the dynamics of the conformal factor of a metric, of a two-dimensional metric. And indeed, the Liouville equation of motion can be interpreted as the constant curvature equation of motion for a metric that looks like this, e to the phi dz bar. So you can think about phi as being the scale factor of the metric. But for me, the crucial point of this action is that it gives a very convenient way of parameterizing the properties of two-dimensional general CFTs. And what I mean by general CFTs, these are CFTs that only have Virasoro symmetry. So I'm not assuming that it's not that's sort of an irrational theory. If you would insert an operator like that in the path integral for the Liouville theory, then this operator creates a local deficit in the constant curvature equation, and a local singularity in the constant curvature equation. So these things are sort of, you can think about either as sort of things that carry a charge, but you can also think about them as something that creates a local curvature singularity. And then these things have a conformal dimension. One slight, maybe annoying thing as well, I'll also use delta instead of h. H is the chiral conformal dimension. Delta is h plus h bar. H minus h bar is an integer because of the single valuedness. For most of the time, I'm going to ignore that integer to some extent. I'm going to focus mostly just on the conformal dimension. But in any case, this thing will have a conformal a value for h, actually. That will be given by this expression. So it's quadratic in terms of alpha, which is indeed what you would expect for a vertex operator. And then it has this Q thing here. Again, Q is sort of is what's called the background charge. Now, it turns out to be convenient if I'm going to be looking at what I call heavy states, or heavy part of the spectrum. Then actually, it turns out that for that in that regime, that this alpha is going to be Q over 2 plus an imaginary thing that we're going to call P. And then this equation here turns into Q squared over 4 plus P squared. So this equation actually corresponds to what I was describing yesterday, that if I want to think about heavy states, the heavy states is where the spectrum becomes very dense. There was this gap where the heavy spectrum started. The heavy spectrum starts when P is equal to 0, which is when alpha is Q over 2, and when the conformal dimension is Q squared over 4. And if you compare it with this formula, this Q squared over 4 is C minus 1 over 24. So this is where the heavy states start. So this is all you need to know actually about Liouville theory for now, that there is this way of parameterizing the conformal dimensions in terms of what we call a Liouville momentum. That's useful. That there is this quantity Q, which we call the background charge. It's related to the central charge. And then there's this number B that sits here, which is the coupling of the Liouville theory. There's all kinds of course, there's a long literature about the Liouville model. There's the famous DOZZ formula that shows how to, that gives you the 3-point function of this theory. People studied boundary states in this conformal field theory. But for me, at least, the main role of this theory is that it's going to parameterize essentially this structure and generalizations of the modular S matrix that give you information about how the conformal blocks, which are sort of the chiral components of the partition functions of the theory, transform when you start changing the shape and you perform one of these modular transformations. Are there questions about this? And as we'll see, this theory actually starts showing up a bit later when I start discussing the SYK model. And it's actually useful to compare what happens in the SYK model with this particular parameterization. Yes, there's a question.
Do we have to worry about what is the physical spectrum, so how we pair left and right moving fields, or it is not important for this discussion?
Yeah, excellent question. And indeed, this question is maybe what has led people to some confusion, which is kind of why I'm calling it Virasoro CFT. Because indeed, if you want to view this as an actual theory, a true CFT, you have to solve the conformal bootstrap equation. Basically, like this is an example of how you kind of quote-unquote solve a bootstrap equation. And that indeed imposes this condition that the left and right conformal dimensions are integers, for example. Now, I can tell you that's already a problem a little bit with Cardy's argument. Because if I plug this equation into here and I write down this integral goes over h and h bar being independent. So this formula doesn't tell me that h minus h bar is an integer. And it's actually a very subtle question, how to make Cardy's argument compatible with the fact that h minus h bar is an integer. In my mind, it's actually an unsolved problem. So my philosophy is going to be more the following, is I'm just going to think about this Lagrangian as a way of parameterizing, as I was mentioning, the modular, if you wish, the modular functor, or the way in which the chiral partition functions of this theory transform under modular transformations. So I'm allowing myself to decompose this thing into chiral sectors. And then the bootstrap is a separate issue.
Is there a bulk analog of these heavy states? A holographic analog?
Yeah, that was my topic of yesterday's lecture.
Okay, sorry.
The bulk analog are the BTZ black holes.
Okay.
So the BTZ black holes have a minimal mass, and that's exactly where the heavy states sit.
So in the context of yesterday's lecture, you were discussing states heavy states that were actually discrete, but in this case, these states form a continuum of states.
Also, excellent question. And this is sort of essential to this sort of the philosophy of what's happening here. So the reason why this region looks a little bit fudged out is because initially I had a formula here where it was summing over h and h bar. And then I decided to rewrite this thing in terms of an integral with a row of h and h bar. Now, if this were an actual CFT, then I should have written down a sum, because typically we expect that the spectrum is discrete. So in that case, this row is a bunch of delta functions. Now, the way we're going to, as you can see with Cardy's argument, he's not going to be able to resolve exactly what where those delta functions are localized. What he can do for you is he can tell you for a small little energy window how many states there are. But in the end, indeed, it looks like this. If I do, because this is actually an exact equation. If I take the vacuum character and I decompose it, and again, importantly, in the decomposition of the vacuum character in the dual channel, only the heavy states contribute. So for a long time, actually, I've complained a little bit to people that sort of said, oh, hey, in CFTs, the vacuum character dominates. No, it only dominates at low energy, at low temperature. At high temperature, it's actually what I call the Cardy spectrum that dominates. And this is really the reason for why Liouville theory, or the vacuum character, quote unquote, is a good description of holographic CFTs, because you have this enormously dense spectrum of states. And then what you're going to do is rather than actually trying to resolve the actual spectrum, you're just going to write down a spectral density. And the spectral density is universal. And let me actually write down in this parameterization what this thing is. S0p, so now I'm going to be labeling it by means of this p, okay? Turns out to be up to some prefactors that are not very important. Sinh of 2 pi p divided by b times sinh 2 pi bp. That turns out to be the modular transformation of the vacuum character. So this is a quick prediction of what the spectrum of a general CFT looks like, because indeed here I tell you what the spectrum is, so I'm labeling the H by that P. And indeed, if you plug in the formulas, this thing leads to the Cardy formula. It also leads to an entropy, a spectral density that's compatible with that of the BTC black hole. So this is a confirmation of the prediction of ADS CFT. Okay, yes.
This is perhaps a slightly tangential question, but with this S matrix, what do we learn from the Verlinde formula?
Yeah, it's only recently actually that people have been able to generalize the Verlinde formula to this irrational case. So there are formulas that are analogous to the Verlinde formula. The problem, I should say, has to do with this funny S matrix over here, that the vacuum character decomposes in terms of the heavy spectrum. And the modular S matrix, in the modular transformation of the heavy states, only heavy states sit on the right-hand side.
Okay.
So there's no modular S matrix that maps a heavy state component to the light state. So there's some funny business going on with Liouville theory that make it different from rational CFTs. But people are starting to understand better how these things sort of tie together. Yeah.
Okay, thank you.
How light operator is described by Liouville action?
Yeah, so how are the light operators disqualified? This has to do with what I mentioned yesterday, is that the light spectrum of a typical CFT is non-universal. So there are special light states, and if I look at different CFTs, we expect that those are kind of different between different CFTs. The part of the spectrum that's universal is the heavy spectrum. So the idea that the bootstrap leads you to formulas that match with Liouville theory has to be sort of put together with this philosophy that people more recently started advocating, is that we should think also about holography as a mapping between a boundary and a bulk, where actually the bulk gravity theory should be dual to an ensemble of CFTs. So if you start taking an ensemble averaging, then basically all the light states average out to 0, meaning you no longer know where they are, so basically they don't contribute. So formally speaking, this theory has has a ground state, and then it has a gap, and then it has heavy states. So this is a theory which you may want to call pure gravity, in the sense that it doesn't have a light spectrum. And this is the only universal part that survives after you do the averaging. So that's the sense in which the light states are sort of disqualified. Most likely, if you start thinking more accurately about the bootstrap, indeed if you start solving the bootstrap equation, you probably are able to show that at least that's my guess, is that there must be light states still in the spectrum for the theory to be self-consistent. But the light states that you put in the spectrum are non-universal. You have to put them in, but at a place that you cannot predict from the bootstrap.
Sorry, just a small comment. The Liouville theory does not have a normalizable vacuum, so does not really qualify as a, can you comment on that? I mean, it's a good auxiliary theory which captures
Correct.
the universal
This is exactly
property.
these are the words that I use.
Yeah. Okay.
It's an auxiliary theory, so I'm calling it Virasoro CFT. The CFT, I don't like the quotation mark too much, but it should be in quotation marks. It allows you to organize the Virasoro conformal blocks in a very useful way. Right. And by the way, the fact that the vacuum character is not normalizable is not a bug, it's a feature. Because it kind of follows from the philosophy that this is an ensemble average theory that's dominated by the heavy states.
Yeah, one simple question, like how do you get the metric?
Okay, speak up a bit, sorry.
How do you get the metric to be this e to the power 5 dz and dz?
Sorry, I can still.
The metric I am talking about, the ds squared e to the power 5 dz dz.
Sorry.
Yeah, ds squared, the metric.
Oh, this one.
Yeah. How exactly, like why it should be like that?
This is more a historical comment. I'm just writing down this theory because it's an interesting theory to study. But it turns out that if you consider another CFT and you put it on a general background with a two-dimensional metric, and you solve for the conformal anomaly, the way in which the partition function depends on the scale factor of the 2D metric, you're going to find this action. And this is what Boykov did in his famous paper in the early 80s. And he found this action, but then his phi was related to the conformal factor in this way.
Thanks.
Okay, so if I'm understanding this thing correctly, as we're saying, this is not an actual CFT, first of all, because of this continuous spectrum in the high energy.
Right.
So I should imagine this more as the output of an averaging over theories,
Correct.
over CFTs.
Right.
So that's also the reason why, I guess, again, the rho is not a sum of deltas. And about the light part of this theory, I mean, in principle, I'm allowed to pick an alpha between 0 and Q, no? That
Perfect.
still gives
Okay.
me
Also,
a positive
very good
H.
question. Yeah,
Like
right.
this.
Yeah.
Actually, if I may add, maybe this has connection to what you will say earlier, this structure really reminds me of the representations of the sitter, where you're kind of describing the principal and complementary series.
Yeah, so it's true that, excellent question. So indeed for alpha small, actually then this H is real for alpha small. But if alpha indeed gets bigger than Q over 2, then I need to do this thing to make it real, because otherwise this thing would go negative. So indeed the heaviest part of the spectrum is indeed, as you said, it's sort of like the continuous series representations. But let me make another comment. And this is actually indeed more evident precisely when you give it the phi field this interpretation. If you solve for the Liouville equation, then maybe I should write it down. So suppose I indeed, by the way, I can remove this R by just taking the metric to be flat, the background metric to be flat, but then the scale factor of the metric still sits there. Then the Liouville equation indeed will look like this. But then, indeed, I could have here, say, a delta function, z minus whatever, some special location. And that delta function corresponds to the insertion of that operator. And then if alpha is small and real, then this is just a local curvature singularity. If you go around it, you just have a cusp. Okay. Now, instead, if alpha is a heavy state, and you try to solve this equation, it turns out that you cannot really solve it with a local operator. It turns out that the local geometry then starts looking kind of almost like this. It looks almost like the Sitter space, although it's actually a Euclidean negatively curved space. So it turns out that in this regime, indeed, I'm calling it a state. I'm not calling it an operator. And this is the point that Seiberg made, is that this Q squared over 4 is actually sort of, it's called the Seiberg bound. If you're above it, then in terms of the local geometry, you should think about it really as a channel in which there's a state that goes there. So states live in this part of the spectrum. Local operators can live in the real part of the spectrum.
Okay, so...
The states and operators are not identified in this theory. This is another feature of Liouville theory, where the states and the local operators.
So you said that
kind of
for
complementary.
big alphas, let's say, or well, complex alphas of this kind, you're saying that the space-time kind of gets deformed in some
Right,
Euclidean
so
ADS-like
the
way.
back reaction of the local operator prevents the cusp from. So a local operator, when alpha is small, it looks like this.
Okay.
And it turns out that you can actually characterize these kind of sort of local behaviors in terms of what we call a monodromy, because you can sort of solve this equation in the standard way. It has to do with what's called uniformization. And then the monodromy in this case is what we call elliptic. So it's what we call an elliptic conjugacy class. This thing is called hyperbolic.
Okay. So there is a discontinuity. Yeah. Okay. So there is a different thing, and
right.
So why do we reject the second kind? Like, why don't we call those states too? I understand there's a very different qualitative behavior. That's very nice.
So states are things that contribute in intermediate channels. And the on-shell equation of this theory tells you that you want to have a negatively curved geometry. And then all intermediate channels basically look like this. And it turns out that those things don't contribute. Another way of saying it is actually that as states, these things turn out to be non-normalizable. So they drop out of the spectrum as states.
Okay. So, they're not regular objects. Okay, thanks.
No, they are regular objects as operators, but they're not regular objects as states.
Yes, okay, yeah, thanks.
Okay. Okay, so now let me indeed start with the SYK model. And as you'll see, rather quickly we're going to find sort of a similar structure, but we're starting from a very different starting point. So the SYK model has n what we call Majorana oscillators. It's a 1D model, so it's just quantum mechanics. A Majorana oscillator satisfies this particular anti-commutation relation. You can think about them as Pauli matrices. And indeed, the Hilbert space of this theory, the dimension of the Hilbert space of the SYK model is 2 to the power n over 2. And again, we're going to take n to infinity. So that's just basically n over 2 qubits, if you wish. But now the interesting thing is that they interact through a Hamiltonian in the SYK model. And part of the philosophy here is to kind of create a dynamics where everyone is almost interacting with everyone else in a way that's kind of random. So we call this an example of a Hamiltonian that scrambles very quickly. If I flip one of these qubits, then and I let time evolve for a little bit, the fact that I flipped a qubit will have influenced the state of many other qubits because of this interaction. The interaction is of order p. So p is not a parameter. And later, soon, I'm also going to be taking p to infinity, but in such a way that the parameter lambda, which I think I'm going to call 2p squared over n, will stay finite. And we'll see later why this particular ratio of p squared over n is a natural ratio to keep finite. Okay, so let me say, maybe see if I want to make one more comment about the Liouville theory, but maybe I'll postpone that for later. Okay, so the J's are random couplings, the Gaussian random couplings. And again, there are two philosophies here. One philosophy is that I consider one of these Hamiltonians with one choice of J, bunch of random numbers, but the random numbers are chosen from a Gaussian random distribution. and you pick one of them, and I call that thing my SYK model. Another philosophy is that what I call the SYK model is the ensemble average over all these microscopic SYK models. So what's nice about the SYK model, it has a little bit of this similar structure. Again, if n is finite, and I pick a particular set of j's, then this theory will have a discrete spectrum. And it has a finite number of states. We'll see if n literally goes to infinity, it's less clear that the spectrum in the n to infinity limit would still be discrete. Probably it's going to be continuous. Certainly, if I'm going to actually perform the ensemble averaging, maybe at that point it even becomes a little bit unclear what I literally mean by the spectrum. But I can kind of define an ensemble average of the spectrum of the individual models, and this will become a continuum spectrum. So this is, again, a toy model of sort of the same structure that we've been talking about up to now. The achievement, by the way, of the SYK model is quite a remarkable one, because I've been talking about two-dimensional CFTs with all these random spectra. ADS CFT is celebrating soon its 30th anniversary, and the number of 2D holographic CFTs that we really know exist is any number, it's 0. We don't know any holographic CFT in 2 dimensions, okay? We imagine that the structure exists and that we can solve the bootstrap equation and find one of them. Here, there's an example of a theory that actually can write down that exists. And essentially, this thing is going to do many of the things that we want holographic CFTs to do, okay? So in that respect, this is a very interesting theory that one can start studying. And we'll start seeing the same structure emerging, but from a way where we actually know that there's an underlying microscopic Hamiltonian, which is this thing. Okay? So how are we going to do this thing? Let me immediately let me still tell you a little bit about the history. For the case that p equals 4, that's sort of the original SYK model. If I do this thing, it's called the double scaling limit. So that's the double scaled model. So indeed, it turns out to be very useful to have this p be a large number. But when p was equals 4, this model was actually introduced in the early 70s as a model of dynamics inside of a nucleus, where basically these were kind of spins inside of a nucleus. Then indeed, Sachdev and Ye in the early 90s were able to kind of partially solve this theory, indeed by introducing sort of a more path-integral way of thinking about this theory. And so I'll go and discuss what Sachdev and Ye did. Sachdev and Ye still had sort of more like complex fermions. Kitaev indeed introduced the model with the Mariana excitations. So let me write down the action of this model. I think there's a factor of 4, 1 over 4 here, but let's not worry too much about that. If I take n Majorana fermions and I give them that action, then canonical quantization will lead at least to this commutation relation. And then, of course, I just write down the Hamiltonian. And let me not spell out the Hamiltonian. I just plug that in the action over there. So this is my Lagrangian for this theory. And suppose that I want to compute the thermal partition function of this theory. And that's sort of what Sachdev and Ye did. And it turns out that rather than trying to do this thing sort of exactly, I try to control this theory exactly, we're going to be looking at a quantity that naturally survives the large n limit. And that quantity is just the 2-point function between 2 locations, T1 and T2. But I don't do the 2-point function of some given collection of 1 or 2 of these things, but I'm going to average them over all I. So this is the quantity. That's sort of a useful thing to look at. And the plan is going to be to rewrite this path integral for the SYK model into a path integral for this variable. Okay. So we will do what's then called basically the disorder averaging. And the disorder averaging is presumably, at least for most quantities that you want to compute, will give you a very accurate answer. But that's indeed the philosophy where I'm saying, okay, I'm going to actually do the Gaussian integral over these couplings. Okay. Now, these couplings are just constants. They don't depend on time. And indeed, each j independently is a Gaussian coupling. So j with different indices are independent Gaussian couplings. So if I do the Gaussian integral, I'm going to be basically getting Wick contractions, if you wish, between the j's with different indices. And after doing that, it turns out that the effect of having this Hamiltonian is going to do the following, is that, and let me, just to save a little bit of blackboard space, what I'm going to do is that after this order averaging, the SYK action will get the following form, where the disorder averaging leads to a bilocal action. Of this form. Yes.
A very basic question. Why is it more convenient to use Majorana fermions instead of, say, Dirac?
Instead of complex? It's a good question. I would say this is sort of the more basic example. It turns out that most of the structure of the SYK model generalizes to the case where the psi's are Dirac oscillators. But then you have to do more work in having the psi's and the psi bars. But it just turns out that this is sort of the more minimal realization. And it's the one that has the least amount of structure. Because as soon as they are complex, it's a little bit this philosophy that I don't want to put any symmetries in the system that I don't need.
How did you get this dimension? I mean, it does not always look like an integer. Are you missing a floor or something on the?
Basically, the philosophy is that the psi's, at least if I give you two psi's, I can realize this algebra on the Hilbert space of one qubit by basically making each of the psi's the sigma x and the sigma y that act on a qubit. So two Majoranas, and this is why Majoranas are famous, basically they're the square root out of a qubit. So if I have n of these guys, I have n over 2 qubits.
But if n is odd, why does that number look not like an integer?
Yeah, so n is even.
So you can't form an SYK out of an odd number of Majoranas?
It's certainly true that I want to have p even, that's for sure.
But why would you want n even?
Interesting question. It may be possible to sort of get some microstructure by thinking about what happens when n is odd.
And secondly, why are you normalizing the...
By the way, I could have done this thing here where I guess I put this thing around it. This is how...
What's a floor?
This is taking the integer value of n over 2.
Why are you...
or plus 1.
Normalizing the ensemble average of the j's like that? Why is there an
why
n
do
by...
I put this junk here? Because actually it turns out that eventually does something more nicely here. Because basically you can have all kinds of different combinatorics in terms of the Wick contractions. Because basically, the number of these couplings, there's a permutation group that acts on this thing.
And when you say after disorder averaging, you get a certain SYK action.
Yeah, so by the way, there might be a coefficient that I have to briefly look up, but okay, go ahead, yes.
What exactly did you do? I mean, so you took the original action with the minus h, and then did you what?
So what I do is the following. So I have e to the minus h, but now in the h is linear in j. in order to arrive here, what I do is I write down a Gaussian factor, a j squared term, and then I have an integral where I have a j squared in the exponent and a j times a bunch of psi's in the exponent. Then I'm going to do the Gaussian integral over j. I complete the square.
I see.
And after completing the square, I get the square of the, basically of this operator, but where the indices are being repeated. And then I have to sum over all the indices.
You're kind of thinking of J as
and then magically, it turns out that it all becomes basically,
so roughly
in
like
terms of
thinking
this.
of the J as a Hubbard-Stratanovich and doing the
yeah,
J.
correct. It's basically. Just making sure that I get the coefficient correct in front of the, give me 1 second. There's some junk still in front of the j squared. I think there might be some coefficient here. But maybe since j is just a number, I'm going to absorb any junk in this number.
I think there might be a factor of n divided. I think there might be a factor of n divided by p squared or something like that.
Yeah, there's some n over p squared in front of this thing. Is that what you want?
You want to take the large n limit. It's
thank you. Okay, so let me put that there. That thing is going to be useful because indeed, so the next trick, what you're going to do is you introduce sort of a Lagrange multiplier. So since there's this particular equation, what you're going to do is you're going to add a term to the action that imposes this equation here as a delta function. And the way you're going to do that is you're going to take this combination and you introduce a field that we're going to call sigma t of t1, t2. And again, this thing is going to be integrated over t1 and t2. If I add this term to the action, initially when I wrote down this g, I was actually making that g to be defined to be equal to this. But now, instead of making g defined to be equal to that, I'm going to make g an independent field. But then sigma is then an additional field whose equation of motion will then enforce this particular trick. So in that respect, this is indeed very similar, again, to kind of a little bit like a Hubbard-Stratanovich thing, because I started with a Lagrangian which had a bunch of interacting Majoranas. But now I managed to basically get rid of all the interaction for the Majorana oscillators because I put it basically into this term. This is my interaction term. Because this action is now quadratic in terms of psi. So I can now integrate out psi just by getting a functional determinant, if you wish. Okay. Okay, are there questions about it? So after integrating out psi, what will happen is that the combination of these two terms will repackage itself as follows. You know what? Maybe I'm just still going to be lazy. I'm going to do it with this thing. Everyone who wants to write down this can write it down. So what's going to happen, the psi is going to, I do the psi integral. I still will have a term that's g times sigma, but the psi integral will eliminate the psi's from this action. And then this thing here will become minus a half times the logarithm of the determinant of d dt minus sigma t1, t2. Okay. And this thing will have a delta function, t1 minus t2.
Sorry, I have a question.
Yes.
This effective theory or this action
right.
is then after integration, is neutral in the fermion number.
Sorry?
Is neutral or even in the fermion number, in the sense that you have always a I don't know how to say that. It's even, I mean, you don't have things that if you
can distinguish the different fermions, is that what you're asking? Sorry.
Sorry?
I cannot, if I have this theory, I can no longer insert operators in this theory that can distinguish the different fermions.
Yes, if you get a minus sign in the fermion, in this theory you can see that this symmetry is not here.
So the fact that these are fermions is still visible from this DDT that's in here.
Okay.
And the Green's function associated with DDT is a step function.
Okay.
Or a sine function, if you wish.
Yes, I think that.
So
yes.
the fermionic nature is still present in this action.
Ah, okay, okay. Thank you.
And indeed, the other one is that, okay, I have e to the minus the action, and I put a minus sign here. So indeed, this determinant, which actually is a Pfaffian, but then I put 1 over 2 here. I take the square root out of the determinant, and it sits upstairs. It doesn't sit downstairs. The Gaussian integral that I was doing was a fermionic Gaussian integral. Again, this is not going to be the topic sort of my discussion too much, because pretty soon, indeed, I'm going to be taking this limit where p goes to infinity with this ratio of finite. So I'm going to reshuffle the thing still a little bit more. And before you know it, this action will actually start, as you'll see, will actually start taking this form. By doing one more manipulation. So this is why I'm kind of limiting what I'm doing here a little bit to the board, because in the end I want to get the effective action for this thing. Yes?
Why is there no n dependence within the determinant? Did you already have a 1 by n in the kinetic term?
Sorry?
I mean, you erase the terms, but like the sigma psi psi had a 1 by n, and the psi del t psi did not have any n. So I'm just a bit confused as to how you got that determinant to not have any n's inside the determinant.
Inside of the determinant. Oh, thank you. Oh, you mean there was a 1 over n in front of the psi psi thing?
Yeah, psi psi sigma had a 1 over n. And the psi del t psi did not have any n's. I think you want to put a 1 by n in the psi del t psi also?
No. Give me a second. I don't think I want to do that. The n sits in front of the determinant, but I don't think it sits inside of the sigma. Of course, any n that sits inside of the sigma, oh, sorry, yes. Yeah, so when I was doing the G sigma thing, I can rescale sigma so that there's actually an n in front of the G sigma. Because it's homogeneous in sigma, I can always put the n here. That gets rid of your n. So and notice the following indeed. There's an n here. There's going to be n here because I have n of my n fermions. So the whole action is going to be of order n, which is a crucial idea of doing a large n approximation, is that your collective theory will have an n in front of the action. So this is the first observation, is that this theory, although it looks pretty horrendous, slowly you start to get used to it, but you can do just the classical equation of motion of this theory that already starts solving the theory at large n.
And the del t is a del t1 or a del t2?
This is a delta between T1 and T2, so there's only one delta. So it sets T1 equal to T2.
No, I'm asking about the derivative. It's not symmetric in T1 and T2, right? Not.
It's not symmetric in T1 and T2, but if I multiply it times the delta function, I think it's fine. By the way, as I said, I'm going to get rid of this thing pretty soon. You have to kind of believe me, because I'm going to do the following. Is that if p goes to infinity, this power of p becomes very big. And it turns out that this particular Green's function will start to behave individually. This is sort of like the 2-point function. I'm going to take the following parameterization. If these were literally free Majorana fermions, then the two-point function would have just been a sine function of T1 and T2. And I'm going to introduce a variable that I'm going to call little g of T1 and T2. That basically gives you the deviation of g with respect to just the free two-point function. I put 1 over p here because you can kind of argue that in this limit, this thing will go very close to this. So this is a parameterization. Then also this thing turns out to be basically a small field. You can introduce a small sigma field. It does this. And now I'm going to make a jump in the derivation for you. I'm not going to write everything out, but it turns out you can find it in various papers. I can give you the references if you are asking me after the lecture. But in any case, next I'm going to integrate out. It turns out that it's going to be possible to integrate out sigma. So the fact that sigma actually itself is also small will allow me to essentially expand this determinant in powers of that sigma. And it turns out that this expression greatly simplifies if you just expand it to second order. There's going to be a linear coupling still between the little sigma and the little g. And rather magically, two things will start happening. First of all, if I plug this in here, then this, for the large p limit, this becomes the definition of an exponential. And indeed, essentially, the sine function will also essentially drop out. So this thing will become dt1, dt2 of e to the g t1, t2 in the large p limit. So that's what the interaction looks like times the pre-coefficient. So this already looks a bit like the Liouville potential. But indeed, it lives in this TT1, T2 theory. By the way, this I should mention that this thing is called the dynamical mean field theory. Dynamical mean field. It's a theory that lives on what you might want to call kinematic space. And what I mean by kinematic space, it lives in the two-dimensional space parameterized by T1, T2. So even though I started with a one-dimensional theory over here, this particular theory, because it has this double integral in here, lives on this kinematic space. Okay?
G as defined was just a sum over psi I, right? So that's P independent. Or are you trying to solve the classical equations of motion to...
Yeah, so this is just a parameterization.
So am I correct in saying that finally capital G or this curly G is P independent?
Right.
Okay, so little g is P dependent, so that is P independent.
Yeah.
Okay.
But I would say this just parameterizes the typical size of the fluctuations in the big G. So it's a parameterization. Again, because of the definition of the exponential, this is what you get. The thing that actually is quite unexpected, if I'm completely honest, it turns out that if you indeed integrate out this little sigma, you plug little sigma in here, and you integrate out little sigma, it turns out that all this junk, which I'm indeed about to erase, just organizes itself in a very simple way.
Is little g symmetric in the time variables?
Sorry?
Is little g symmetric in the time variables?
Yeah, so this thing is anti-symmetric in T1 and T2.
Ah, right, yeah.
So this thing is now symmetric in T1 and T2.
Thus justifying the signum.
Also, since these are Majoranas, G is real. And that's part of the reason why it's symmetric. So anyway, I just gave you the outline of the derivation. The upshot of all of this is the following. So I'm going to erase all of this, and I'm going to write for you what the dynamical mean field theory looks like. But again, the dictionary. Yes.
So sigma has no constant. I mean, it starts with 1 by p.
Right. So sigma is sort of the equilibrium value of sigma is equal to 0. And therefore it has no constant in it. Whereas the equilibrium value of G is the free propagator of the fermions. So that's why this sign function naturally sits there. So the upshot of all of this is the following. There's going to be an action. Maybe there's a 4 here. I have to think about that. For now, I'm just putting n over p squared. dt1, dt2. d1 of G, dt1. So let me just call that d1. d2 of G plus j squared. And this depends on t1. So we started with something ugly, but we ended with something pretty. Where, indeed with the dictionary, this is the 2-point function. After the dust settles, the action in terms of this little g looks basically like the Liouville action. You can see now why it's actually interesting to keep this p squared over n finite. Because this is now going to be a Liouville action with a coupling constant that's governed by that combination of n over p squared. This 1 over p squared has something to do with the fact that we're putting these p's here. But it's sort of, it's the natural thing to do because that also, the p over here was necessary to have coefficient 1 in front of this g. If I would not have put the p there, I would not have the coefficient 1 in front of that exponential.
So in Liouville, the cosmological constant, that parameter mu, is an irrelevant parameter.
You can always absorb it in a shift of phi.
Right.
That's right.
And you can derive a KPC scaling from that. So here, that mu would be the j squared. Does that correlate?
Correct. Good question. For now, this is just an action. But it's true that j is the only thing that introduces a scale in the whole problem. So if I choose my units appropriately, I can put j equal to 1 if I wish. That's just the thing that sets the energy scale. You were talking about KPZ scaling. Again, I didn't yet talk about Liouville theory as a theory of gravity, which is kind of where KPZ scaling comes in. But actually soon we will be talking about Liouville theory as a theory of gravity as well. But right now it's just comparing the two Lagrangians. Okay. Are there more questions? Yeah.
The statement that that you get a Liouville in the kinematic space is true for any distribution of the j parameter seemingly, because you just assume
it's only if it's Gaussian, for sure.
Where did we need that fact? Because we seem to have only needed the second moment to be finite.
I was doing the Gaussian integral to really derive this action because I got this bilocal theory. For example, if I have a cubic correlation between the j's, I probably get a theory that involves 3 of a triple integral. So I have to be more. Yeah, I certainly have to be more. So the Gaussian integral is essential.
Thanks.
This effective action doesn't look positive definite because you have a product of 2 derivatives and you can make one of them negative. So it seems like...
you mean this thing here?
Yeah.
Yeah, I can talk about this thing a bit more. This thing actually looks indeed like a kinetic term in 1 + 1 dimensional Lorentzian signature. So it looks like it lives on this kinematic space. I started indeed with a theory that only had time dependence, but now I get this theory that has 2 times. But the kinetic term looks off diagonal in the T1 and T2. And this will actually turn out to be quite important. I've been working sort of in actually in the end I'm going to be working in Euclidean time. And in the path integral, this action is really an e to the minus s, so there's no factor of I in front of the action. And there's going to be a bit of tension between the fact that the coefficient of the action is real, whereas the kinetic term is going to be Lorentzian.
Sorry, just a basic question maybe. I'm not sure I understood how you integrate out the little sigma.
Yeah, I jumped a little bit. But in words, what happens is there was this ugly determinant. It turns out that ugly determinant, if you expand it in the regime where the big sigma is small, it turns out that you can actually write down that determinant again as a double integral. It turns out that because of the fact that there was the ddt in the determinant, turns out that there are indeed some step functions in that integral. And so it becomes quadratic in sigma integrated against some step functions. And then if you integrate out sigma, because there's a term sigma times g, somehow magically it produces this kinetic energy for g. I'm not going to write out all the steps, because otherwise I don't have the time to do what I need to do. Again, this is explained, at least it's been developed sort of like 6, 7 years ago, or 8 years ago, that indeed it was recognized that in this limit, the action simplifies like that.
This is a question about the Euclidean nature of T1 and T2, as you are mentioning right now. If we were to continue it to the Lorentzian regime, we have to weak rotate both T1 and T2. And
right, yeah, right.
In
so
which
there's no
case,
factor, so that it doesn't help with factors of I. That's right.
Yeah, so is there any nice Lorentzian interpretation that one can ascribe for
yeah, so let me just, I think the comment I would make sort of is more the reverse. Is that regardless of whether you think about t as real time or as Euclidean time, again, this term will look like this. There might be a sign change between Euclidean time and real time. But as we'll see in a moment, the important prefactors are actually factors of I in a moment. And those do not depend on whether you are in Lorentzian or Euclidean signature. The philosophy often is going to be the following, is that we're going to be doing thermal correlation functions, and then time is Euclidean. But then we work in sort of, can also go to a real-time formalism, where we then analytically continue the Euclidean time to Lorentzian time.
Perhaps another question is there any nice notion of unitarity in the Lorentzian picture, or is it manifestly lost because of the disorder averaging?
Good question. Also, the disorder averaging makes, of course, the Hilbert space formulation a little bit less clear. My philosophy is still the following, is that in principle what I'm describing here is still the microscopic theory. In my mind, actually, perhaps even just with one chosen value of the J. But if I'm asking questions that are sort of more of an average nature of the theory, then this particular Lagrangian is actually a good way of computing those quantities. So I know for a fact still that I'm working in a unitary theory, even though this effective description by itself may obscure the unitarity somewhat. But in this effective description, I can only look at sort of, how should I say, ensemble average quantities, and also things that are actually large n averaged. Because indeed I have this average 2-point function.
Thank you.
Okay, there was something I wanted to say, but then I forgot what it was. Oh yeah, now I know what it is. So I called this thing the kinematic space. There's one important thing still that I should mention. Suppose we do this indeed at finite temperature, then T1 and T2 are actually periodic. And then it's actually perhaps convenient to think about, say, T1, and let me call it, yeah, so let me call it tau 1. And no, tau is not a good name either. T1 and T2, let's call them still Euclidean time, and they are periodic. So the kinematic space indeed is two intervals between 0 and beta. If I do finite temperature correlation functions, I have periodicity in beta. But then there's a line where T1 is equal to T2. Let me draw that line here. Now, when T1 is equal to T2, the G T1, T2 at T1 equals to T2 is actually equal to 1. And the reason for that is that my Majorana fermions square to 1. And therefore, the Green's function at T equals 1 is equal to 2 is actually equal to 1. Which means that this G, T1, T2, is equal to 0 on that line. So that's a boundary condition. So this theory lives on this particular quadrant, if you wish, where there's that boundary condition that T1 and T2 must be 0. Now, by the way, there's a whole, so now the question is, can we solve this theory? And it turns out that we can, actually quite simply. In a slightly surprising way, it turns out that this theory is easier to solve than that theory, but I'm still going to make a few comparisons. Because essentially, the methods that people use to solve this theory kind of are a little bit similar to the ones over there, but people run it through a little bit more trouble. The basic idea is actually very simple, is to just try to expand that exponential. So basically, I'm going to try to do this theory by putting it in the path integral and just doing a Taylor expansion of this interaction term. If I drop the interaction term, then this is just a free theory. And I can just do all the necessarily Wick contractions with this, the propagator of this theory, with having a bunch of exponentials in here. So that's one way of trying to solve this theory. And that leads to a structure that's called a chord diagram. Where essentially I'm going to be thinking about indeed correlation functions on here. And the way I'm going to draw them is I'm going to think about them, and again, as living on a circle, where this is the thermal circle. So I'm rolling this thing up in a circle. And a point in this thing here, this point here, corresponds to a pair of points over here. And if I put an e to the g at that point, it kind of corresponds to the 2-point function, or actually, it corresponds to putting an operator here at T2 and T1. And it turns out that the contribution of this thing to the partition function, indeed doing the Taylor expansion, having a gas of these things sort of inserted in the plane, doing the integral, basically I end up doing essentially Wick contractions between these points T1 and T2. And this thing here is called a chord. Now, microscopically, if you remember, this e to the g was actually a pair of Hamiltonians, meaning it was obtained by doing the Gaussian averaging of the J over the J field. So what this chord actually represents, it means that I have an insertion of the SYK Hamiltonian at the location T1 and an insertion of the SYK Hamiltonian at the location T2. And I'm essentially doing a Wick contraction between these two Hamiltonians. Now the Hamiltonians look like this. And now why would I be doing a Wick contraction? The reason I would be doing a Wick contraction is, again, because I do this Gaussian integral over J. That leads to a Wick contraction between J's. The psi's, and that's part of the idea here, is the psi's in this expansion are also just free Majorana fermions. And I can just do the propagators for the individual psi's. But because of the large n limit, the psi's actually have to follow the same index structure as the j's do. So therefore, if one j Wick contracts with another j that sits there, then also the corresponding psi's have to do this thing. So that's basically what this chord is going to be. It's going to be the Wick contraction between the Hamiltonians. And it turns out that you can basically sum these things and get an exact answer for the SYK partition sum. I'm going to do that in a moment, but before I do that, I want to still learn one more lesson, and that's I want to compare, again, this action with the one over there that I wrote down over here. And we're going to see a funny thing happening. How am I doing with time? I have like 15 minutes. No, I'm done. Can I take 5 minutes? Okay, I can wrap up in 5 minutes. So as I mentioned, this thing is Lorentzian signature. The pre-coefficient is real. So to some extent, if I think about this as a Liouville action, the Liouville coupling is actually imaginary. And that's very important for the property of this theory. So this thing here is an imaginary, if I compare it with this. So this theory lives in Euclidean space, and the pre-coefficient is also real. This thing lives in Lorentzian space, and the pre-coefficient is real. So the way I should make the dictionary between this side and that side. So by the way, so I'll continue this discussion this afternoon and tell you how to solve it. The final comment that I'm going to make is the following, that in the comparison between that theory and this theory, I should do the following. I should identify that Liouville theory where the pre-coefficient n over p squared should be compared with the 1 over 2 pi b squared. Okay. So b, but now, because of the fact that this is the Lorentzian signature, I should put a factor of I here. So b squared is going to be imaginary. Yeah, this is the Euclidean action. Sorry, here? Yeah, as I said, at the moment I'm not going to pay attention to pluses or minus signs. I'm going to only pay attention to factors of I. Because as you'll see in 1 second, and this is the last formula I'm going to write down and then we're done, if b is imaginary, then b indeed is b squared is imaginary, then this is e to the plus or minus I pi over 4 times some other number that I'm going to call beta. Beta is maybe not a good name. I'm still going to call it beta. Okay. It's not the temperature, but it's just, you know what? The solution to this equation that b squared is imaginary is b plus minus is this thing times a number that I'm going to call b. And that number b is now real. And you can express this number b in terms of that n over p squared, but the important comment that I want to make is that this Liouville theory has a Liouville coupling that looks like that. And now if I plug it in here, and this is your homework between now and the afternoon, is that when you plug this value of b in this formula for the central charge. It turns out that Liouville theory, if I think about it as a conformal field theory, it has a complex central charge. And it actually has a very interesting value for the complex central charge. It's going to be equal to 13 plus or minus 6 times that b squared minus 1 over b squared. Times a factor of I. So it has a complex central charge equal to 13 plus an imaginary piece. And this is something that should at some point start really ringing a little bit of a bell, but I'll make use of this result in the afternoon. Okay, thank you.